So it's a great pleasure to introduce Ravi Shankar from University of Oklahoma, speaking on highly connected submanifolds, non-negative curvature, and the leaking form.
Okay, so for those of you who are hoping to hear Martin, this is your chance to get away. And screen is, oh, there we go. So I'm just, think of me as a placeholder. Perhaps some of the things I'm gonna say at the beginning is also what maybe Martin was gonna introduce in terms of background. And if it just keeps going and Martin doesn't come back, and then at some point I'll just stop and give you an idea, because I certainly didn't prepare the things that he eventually wanted to talk about. So feel free to stop me with questions. So as Martin was perhaps trying to start out by saying that we are looking at complete Riemannian manifolds with non-negative sectional curvature. And this is a class where, you know, some things are known, but there's also a great bit of mystery about them, what kind of manifolds are in here and what are not. And so I'm sorry if I'm stumbling a little bit. I certainly didn't come prepared to give a talk. In any case, we have, we can break this up into two categories of compact manifolds or non-compact manifolds. In the non-compact case, we have the beautiful theorem of Cheeger and Gromol, which states that an open manifold, meaning complete non-compact Riemannian manifold with non-negative sectional curvature, inside it there's something called SOL, a complete, totally convex closed submanifold, so that the whole manifold is diffeomorphic to the normal bundle of it. So all the topology is contained inside a SOL of this manifold. I say a SOL because sols are not unique, but they're isometric to each other. So from the point of view of topology, since we're trying to understand what kind of topologies that can occur, we will, at least for the purposes of this talk, restrict ourselves to closed manifolds with non-negative sectional curvature. But I will point out that in the non-compact case, the inverse SOL problem remains a big open problem. Some partial results are known, of course, but the big problem still remains widely open, namely which vector bundles over closed manifolds with non-negative sectional curvature themselves admit non-negative sectional curvature methods. So suppose we do look at closed manifolds with non-negative curvature. What are some obstructions? Perhaps the most seminal theorem in this line of inquiry is the theorem of Gromov, which basically says that if you look at the total Betti number of such manifolds, then it's bounded above by a constant which only depends on the dimension. Now, of course, that bound is kind of nuts. I mean, super exponential bound. But, I mean, the conjecture bound is 2 to the n, namely that's the torus, which basically says, to put it in really concrete terms, as an example, let's say in dimension 4, if you take enough connected sum copies of CP2s, then this cannot admit non-negative curvature, which is a remarkable result, right? Also point out in dimension 4, the conjecture bound is 3 copies of CP2 do not admit because of something else called the Bott conjecture. But which is a little bit qualitatively different from, say, Ricci curvature, because Shah and Yang showed in the 90s that any number of copies of CP2 admits positive Ricci curvature. And then there are other obstructions. So, for example, Cheeger and Gromol showed in the non-simply connected case that the fundamental group has a abelian subgroup of finite index. And then again in the non-simply connected case. So this was a precursor to the Gromov's big theorem that I first mentioned, that the fundamental group has a generating set with a bound on the number of elements, so the bound only depends on n. And this is my favorite proof. The proof is like 4 or 5 lines. I encourage you to take a look at it. Absolutely beautiful application of Cohomogeneity theorem. So now we come to, well, we have obstructions. So how do we construct such manifolds? So the simplest thing is if you have two such manifolds, then the product metric also has non-negative sectional curvature. That's sort of the easiest thing you can do. So product of any two spheres, for example. Somewhat more complicated and perhaps one of the most useful results in this line of inquiry is if you have a Riemannian submersion and if the manifold M has non-negative sectional curvature, then so does the manifold B. So if you have, this is because of the Gray-O'Neill curvature submersion formulas that tells you that sectional curvature is non-decreasing for submersions. And this is, by the way, one of the key idea in almost any construction that we know of today. And then all the way back in the 70s, Cheeger already showed that the connected sum of any two compact rank 1 symmetric spaces admits non-negative curvature. And if you might wonder, well, can you take the connected sum of any two non-negatively curved manifolds? And unfortunately, no one's been able to make that work. And also, if you could do that, you could produce a counterexample to the Bott conjecture problem. So Cheeger's construction is very special. It has to do with the structure of symmetric spaces, and a version of that, a more advanced version of that, is coming up later in what's called the Grove-Ziller construction. And since I mentioned Grove and Ziller, about 20 years ago, Grove and Ziller showed that if your manifold is cohomogeneity one, namely it admits, if you have a manifold M and a group G such that G acts on M with principal orbits of codimension 1, or alternatively orbit space which is one-dimensional. And furthermore, with the additional restriction that the singular orbits are of codimension 2, I'm assuming here that both M and G are compact, so that the orbit space is a closed interval. Then in this case, they showed that using a clever construction that the manifold can be real. I mean, it was known it can be realized as a gluing of two disk bundles, and then they were able to put the right metrics on each half of the disk bundle and glue it and still retain non-negative curvature. And I should point out, like I said before, all these properties use the Gray-O'Neill submersion formulas, the contraction property, and Lie groups, because they form the largest, easiest known class of non-negatively compact Lie groups. Form the largest, easiest known class of non-negatively curved manifolds. So what are some examples? So if you take a simple compact Lie group, then killing form on this Lie group induces a bi-invariant metric by translating it around. And it's not too difficult exercise to check that this gives you non-negative section curvature. The curvature depends on the Lie bracket in this case. And therefore, if you put that together with the Gray-O'Neill subversion formulas, if you take any coset space and you push down the metric from the Lie group and deem your submersion to be a Riemannian submersion, then the induced metric on the coset space also has non-negative section curvature. So sort of a prototypical example is if your group is SON plus 1, and you mod out by the subgroup SON and take the induced metric, you get a round sphere. So these are what are called homogeneous spaces, G mod H. So this, of course, was well known classically for a long time, and then of course there was the Cheeger construction of the connected sum of some things like this, symmetric spaces. So in '74, Gromol and Meyer showed this particular example. So what you do is you take the Lie group G, which is sp2, is 10-dimensional, and rather than act on G with a one-sided action like you would do in the coset space example, G mod H, you look at the subgroup K, as shown, which is actually a subgroup of G cross G. And then you act on G by a two-sided action. So multiply on the left by the element K1 and on the right by the element A2 inverse, so it's still a left action. And unlike the coset space example, when you write an action down like this, it's not automatically free. Sometimes it is, sometimes it is not. In this case, it is. And so you have a two-sided action, and the resulting space is a double coset space. And what you get when you mod out by this K is you get a four-dimensional manifold, and they show in their paper, it's very easy to show, it's actually S4. And so if you mod out by any subgroup of K, in this case, they take the diagonal subgroup, you get a 7 manifold, and you get a fibration where the fiber is S3 and the base is S4. And Milner had written this lovely paper about 20 years before about S3 bundles over S4. And then they show that this particular manifold is classified by these two numbers, 2 and -1 in pi 3 of S4. S3 bundles over S4 are classified by Z cross Z. So these two numbers tell you what the manifold is. And such manifolds are called biquotients. And if you apply Milner's little trick, you see that this manifold is homeomorphic to the seventh sphere, but not diffeomorphic to it. You don't even need too fancy an invariant, just Milner's lambda invariant will tell you that this is not diffeomorphic. So this was remarkable because you get an exotic sphere, which is non-negative sectional curvature just by taking a bi-invariant metric on SP2 and pushing down by submersion, you get non-negative curvature on it. And the key to note is that Borel had shown probably in the 50s that if you have a homogeneous space, which is homeomorphic to a sphere, then it must be diffeomorphic to it. Meaning that you could never get an exotic sphere by the coset space construction. So this was a genuinely larger class of examples that Gromol and Meyer had shown. So these are the so-called biquotients. So of course, biquotients led to a lot of work, including producing several examples of positively curved manifolds, pioneered by Eschenberg and then also by another class by Bazaikin. And then it kind of, all right, the question was, what else can you do? Right? And I should add that people look specifically for exotic spheres, and then Kapovich and Ziller, and also independently Trotaro, showed that among all possible biquotients, there's only one that's an exotic sphere, and that's the one that Gromol and Meyer found. So I hope they played the lottery the day they found it, because that was the only one. Okay, so cohomogeneity one manifolds. So in the 90s, Carsten Grove and Wolfgang Ziller were studying cohomogeneity one manifolds, namely manifold M with a group action G such that the orbit space is one-dimensional. And they were specifically looking at the case when M is compact and G is compact. So in that case, there are two possibilities. The orbit space could be a circle or a closed interval. And the circle case is less interesting from the point of view of topology, and also trying, if you want to get simply connected manifolds M. So the case when the orbit space is a closed interval is far more interesting. So in that case, what happens is Mostert showed in 57 that you get that. So it was known from the theory of group actions that you have three orbit types. So the part that corresponds to the open part of the interval is the principal orbit type. These are all hypersurfaces inside your manifold M, codimension 1. And then the two endpoints correspond to singular orbits, which are smaller dimensional orbits. And they correspond to three conjugacy classes of subgroups. So there's the principal isotropy group H, and the singular isotropy groups here, which are called K plus and K minus. And Mostert showed there's this beautiful way to put them together using the slice theorem. Your M is actually a union of two disk bundles. So cleverly chosen disk bundles, and then equivariant disk bundles with the appropriate action of K plus and K minus. So you get the boundary is this G mod H. And from the construction, it follows that K plus minus mod H there's a relationship between these isotropy groups, are spheres. So this is a necessary condition for, for a picture like this. And Mostert also showed, this is the remarkable fact, that you can start with an abstract group diagram like that looks like a diamond, G, K plus minus H, with the condition that the representation of H into G, or the homomorphism of H into G, factors correctly through K plus minus, and K plus minus mod H are spheres. Then you can actually build a manifold M with a group action G with that diagram. So it's a one-to-one correspondence between group diagrams and cohomogeneity one manifolds with such an action. So this is beautiful structure, both algebraic and geometric. So what does this help us with in this case? So while Mostert's theorem was known, what Carsten Grove and Wolfgang Ziller did is, so you have a cohomogeneity one manifold, there's a group diagram that I was talking about. Then in the special case where the singular orbits are as big as they can be, right? So I'm kind of skipping over things like exceptional orbits because they don't arise. I don't want to get bogged down by that. But as big as they can be in this case would be where K plus minus mod H are circles. So they are themselves codimension one in the principal orbits. Then they were able to show that every such manifold admits an invariant metric, invariant under the action of G, with non-negative sectional curvature. And as a corollary, they were able to show, I mean, there's many results in their paper, but one of the striking results is that every S3 bundle over S4, which includes 11 out of 15 homotopy spheres, admits non-negative sectional curvature. So some of you might think, wait, there are 28 homotopy spheres in dimension 7, and you are correct. It depends on how you count. Like many things in life, if you pay attention to orientation, there are 28 homotopy spheres. If you disregard orientation, there are 15. So you can think of it as 20 out of 28 oriented homotopy spheres are S3 bundles over S4, or 11 out of 15. Either way, all these exotic spheres, where only one was known until then, admits non-negative section. Maybe this is a good time to pause for a moment and ask, are there any questions? You should also ask, is anybody still there, or did everybody leave? Or, you know, it's very hard to give a Zoom talk because
we are still here.
Can't see your audience. Okay, so I'll keep going. Please feel free to, you know, unmute your mic and stop and ask me any questions you may have. Okay, so that was about 20 years ago with the construction of Grove and Ziller, and they were able to greatly expand the known list of topological types. So with regard to Martin's potpourri, your potpourri got, you know, a new flavor, if you will. So what I would like to do is show you a little bit about how, you know, how the Grove-Ziller construction works. So it's a very clever idea. What you do is if you look on the right, you see there's the cohomogeneity one, a particular cohomogeneity one action of the group SU2 on S4, and that's the group diagram. So K plus minus are the pin groups. So I'll explain what PJN means in a second. So pin 2 is simply the normalizer of the maximal torus in S3. It's just two copies of the circle. Q8 is the finite, beautiful finite quaternionic group. And what PJN is actually an artifact of Martin's Irish creativity. It's, if you look at the bottom, so pin is simply you take e to the I theta, and then you take e to the I theta times j. That gives you the two components. And what pjn is, you take e to the j theta, and then take I times e, sort of this other circle and its counterpart. And what Grove-Ziller do is they take this cohomogeneity one manifold, the S4, and then they take a principal SO4 bundle, or almost effectively S3 cross S3 bundle over it. And you have lots of choices of such bundles parameterized by these integers A2, A3, B2, B3, which simply tell you all possible ways of embedding these two A plus minus groups inside these two extra copies of S3 that you just picked up. And what this does is it does several things at once. So it creates a large class of 10 manifolds here. So note that they are all cohomogeneity one. They are all principal S3 cross S3 bundles over S4. And the most important part is the codimension of the singular orbits has not changed, because the lower part of this diagram has not changed into Pj and 2 and 2, 8, which tells you that if you started with codimension 2 singular orbits here in S4, you remain with codimension 2 singular orbits in this class of manifolds P10. So you may apply the Grove-Ziller theorem again to this class of 10 manifolds, and you get for free that this entire class of 10 manifolds has non-negative section curvature. So what you've done in one fell swoop is you've created non-negative sectional curvature on several principal SO4 bundles over S4. And then if you play with these integers and study the topology like they do in their paper, you see that you in fact get all non-negative curvature on all principal SO4 bundles over S4. And then once you have non-negative curvature on any principal bundle, you can take the associated bundle, which is just taking a product and a submersion, and both of those preserve non-negative curvature. So you automatically get that you get non-negative curvature on every S3 fiber bundle over S4 with structure group SO4. So that's sort of the roadmap to their results. But this is the Grove-Ziller construction. To repeat, you start with the specific cohomogeneity one group diagram for S4, and you expand it to a cohomogeneity one group diagram on a class of 10 manifolds, which are all principal S3 cross S3 bundles, parameterized by these four integers. And these integers have to be 1 mod 4 so that Q8 embeds correctly inside of these two new copies of S3 cross S3. I'm making a big deal about it because it's a complicated diagram, and it's going to be juiced up a little bit in the coming slides. So, as I already mentioned, you get all principal bundles this way as cohomogeneity one manifolds, and they all admit non-negative sectional curvature, and therefore all associated bundles. And this is what I said: you can take the principal bundle, take a product with the fiber, and then mod out by the diagonal action of the structure group, and then you get all S3 bundles over S3. So all Milner's so-called Milner spheres get non-negative section curvature. So just to recap, our examples of non-negative section curvature include homogeneous spaces, biquotients, Shiger manifolds, Grove-Ziller examples, products. So is there anything else we can do? So we're going to rewrite the Grove-Ziller construction in the following way. So you have your manifold M, which is this associated bundle, P10 across the fiber, and want the diagonal action of the structure group. But it turns out this can also be written simply directly in terms of an action on P10 without any reference to the fiber S3, namely by taking since S3 cross S3 acts freely, then any subgroup acts freely. So I just take the diagonal action of this S3 subgroup. And when I mod out, one can show you still get the same space. So the important observation here is in the second description of M7AV, there's no reference to the base S4. If I had such a P10, I could mod out by a diagonal action, and I'm not worried about the S4. So the reason this is somewhat critical is that even though the Grove-Ziller construction is about cohomogeneity one, once you've taken this associated bundle, this M7AB, this manifold that they construct, it's not cohomogeneity one, but it has a lot of the same properties as cohomogeneity, namely it admits a codimension one singular Riemannian foliation by biquotients. It has non-negative sectional curvature by Gray-O'Neill. It admits a double disk bundle decomposition. So it has more or less all the same properties as cohomogeneity one manifolds without an explicit large group acting on it. So quite some time ago, Burkhardt-Wilking had this idea: if you take a cohomogeneity one group diagram, and these singular groups that come in a cohomogeneity one group diagram, he said, why not replace them by groups that act freely via a biquotient action? So putting together the biquotient construction and the cohomogeneity one construction in this clever way. So of course, this is a very nice idea, but what the real power of this idea is that this juiced up space that you have with this diagram G, K1, K2H is not totally random. It is in fact a quotient of a cohomogeneity one manifold. Of course, Burkhardt knew this. He's pointing out that there's this thing called the Eschenberg trick, where you can replace G by G cross G, and this diagram on the left here is a cohomogeneity one diagram, and it's a principal G bundle over this manifold that you're trying to construct. So you can sort of see where this is going. We're kind of putting together cohomogeneity one non-negative curvature by quotients and trying to see if you can come up with something new. So what we're going to try and do is generalize the Grove-Ziller construction, and this is kind of the starting point of a lot of the work that Sebastian, Martin, and I did over the last few years. Maybe this is a good time to ask, is Martin back in any shape or form? I'm guessing not.
No, I don't think he's back, Ravi.
Okay, and you haven't heard anything from him?
Feel free to go ahead.
Okay. So let me remind you again, the Grove-Ziller construction and the remark that I made where I'm looking at this associated bundle via this diagonal action, right? So I started with S4, I moved up to manifold P10, S3 cross S3 bundle, and then I'm coming to this manifold M7 that they constructed, but through this idea of taking this diagonal S3 action, this 1 cross diagonal S3. Okay. And the various parameters they had were 1 in the first coordinate for the embedding of pin 2 in the first factor of 3 copies of S3, and then A2, A3 for pin 2, and B2, B3 for PJN2. Right? And this is their entire construction laid out in the framework that we just developed. Namely, you have cohomogeneity one, you mod out, and then you get this type of manifold that Burkhardt suggested, namely cohomogeneity one type of diagram, but with biquotients. So what we're going to do is now generalize this by replacing the first embedding by not just the integer 1, but some arbitrary integer a sub 1, still with the proviso that a1 and b1 are 1, 1, 4, so that we still have the proper embedding of q8, and try and play this game again. Okay. Now, of course, you can't just stick in a1 and b1 because you feel like it. You need to know that the resulting thing is a free action, namely this action of diagonal S3 is a free action. And so the point is that when A1 and B1 are not both 1, the full S3 cross S3 no longer acts freely. And the quotient by S3 cross S3 for the 10 manifold is a 4-dimensional orbifold. And because it doesn't act freely, if you had a free action of 1 cross diagonal S3, the resulting manifold is no longer necessarily an S3 bundle over S4, which is a good thing if you want to get more general examples. And this is the most crucial part, you still get a free action of this diagonal S3 if these GCD conditions are satisfied, which is excellent because it tells you that you're not forced to have 1 in that first coordinate. Okay, so we took the Grove-Ziller construction, we juiced up this first coordinate, and suddenly we get what looks like a larger class of examples. But of course, it remains to be seen from the point of view of topology what we do get. So we showed that when you do have this larger class, where you take now the 6 integers, A1, A3, B1, B2, B3, with the GCD condition, then you get these 7 manifolds, which we call codimension 1 biquotient foliations. And while some of you were there in Münster when we did it, like Ramiro and others, we did try bravely to come up with other names, but they were immediately shot down by the entire geometry group at Münster. First we called them sausages, but that didn't really take.
That was horrible, Ravi. That was horrible.
Thank you. And actually, Sebastian wanted to call them Italian sausages. His point was that when you're foliated by homogeneous spaces, those are like German sausages, but biquotients are inhomogeneous, so they're Italian. But I'm getting sidetracked here. As a vegetarian, this it means nothing to me. So anyway, more importantly, these codimension 1 biquotient foliations are, in this particular case, there are 2 connected 7 manifolds. They admit non-negative sectional curvature because, if you recall, they came from cohomogeneity one manifolds with codimension 2 singular orbits, and then pushed down by a Riemannian submersion. And the fourth cohomology, so it's 2 connected 7 manifolds. So the besides 0 and 7, the only non-trivial cohomology is in H4, which is a cyclic group of order Z mod n, where n is given by this determinant that you see. And we are, of course, interested in the case to have 2 connected 7 manifold where n is not equal to 0. So that could happen, and that's sort of an untouched area of the work that we did. What happens when you get things that cohomologically look like S3 plus S4. We haven't touched that because a lot of the differential invariants and so on that we computed, first of all, we don't know how to compute in those cases, and the theorems also are not quite right in that. So we're assuming n is Z mod n is a finite cyclic group. Okay. And what we also show after computing these differential invariants is that you get a much larger class of manifolds. In particular, if you look at this family with these integers that are shown -3, -3, 1, 1, L, where L is 1, 1, 4, and these are all homeomorphic to 7, since you can compute that n is equal to 1 in this case, in absolute value. And well, so what, right? I mean, how do you know that you get things that are not S3 bundles or S4? So in order to do that, you need to compute differential invariants. So what is the Eales-Kuiper invariant? So if you take, if you have an 8-dimensional smooth-oriented spin manifold, you have, this is, this goes back to the 50s and 60s, the remarkable work done in algebraic topology. You have the so-called A hat genus, which is defined as, for such a manifold, you have a signature form in the middle cohomology. So you take the first Pontryagin eigenclass, and then you square it and apply it to the fundamental class X, and then you take 4 times the signature, and you get this invariant called the A hat genus. So here X is, as I mentioned, the fundamental class, E1 is the first Pontryagin, rational Pontryagin class, excuse me. And then you have the signature quadratic form on H4. And if you take the long exact sequence for a pair, W and M, where W is an 8 manifold and M is its boundary, so for a manifold with boundary, Eels and Kuiper showed by that, you know, this, if you look at the formula down here, it looks exactly like the A hat genus. It's like a pullback of the A hat genus. They showed that you can pull this back via the long exact sequence in cohomology, and you get this invariant, the Eels-Kuiper invariant, sitting inside of Q mod Z. And they showed this is a diffeomorphism invariant for two connected 7 manifolds. So you might ask, well, does this co-boundary, this 8-dimensional co-boundary, does it exist? And in this case, it does. So as I was saying, this co-boundary exists because of the theorem of René Thom. Okay. And Milner showed that the right-hand side is independent of the choice of co-boundary, which is good, so it means it's well-defined. It's additive with respect to connected sums, with respect to orientation, and it classifies, and Ilse Kuiper showed that it classifies homotopy 7 spheres up to orientation preserving diffeomorphism. I saw kind of a notification pop up. Are there any questions? Oh, Martin is back. Martin, are you back?
Yes, but continue. I didn't realize that you lost me right until just now, and in fact, I gave the entire talk. It was excellent.
It was epic.
Yeah, but continue. Sorry, everyone.
No, I was just a placeholder. You want to take over? I only talked about the C1BF construction, and
no,
I can wrap up this page here, and I was then going to talk about the linking form.
No, you should continue. You should continue.
It's more interesting with the fundamental group stuff. So.
No, just continue on.
Okay. So the Ilse-Kuiper invariant classifies homotopy 7 spheres up to orientation preserving diffeomorphism. And you can see when I mentioned earlier, there are 28 smooth structures on the 7th sphere, and it kind of just ticks one after the other, and you get K over 28 in Q mod Z. Okay. Now, the formula shows you that you need this 8-dimensional co-boundary in order to compute this Ilse-Kuiper invariant, at least in some reasonable way. The big problem in this subject is that there's no algorithm or a way to find this 8-dimensional co-boundary. So Thom's theorem tells you it exists, but we have no way of finding it. So what happens when you have a 7 manifold? You know it's a two-connected 7 manifold. Right? If you know it's an S3 bundle over S4, you can take its disk bundle. But if you don't know what it is, how do you compute it? So using the celebrated Atiyah-Patodi-Singer index theorem, Krek and Stolz showed in the 80s that there is a fairly difficult but clever way to do this without appealing to an actual co-boundary. So there's an alternative way to compute the Ilse-Kuiper invariant using what are called these eta invariants. And I'm not just going to read from the slide. I'm just going to pause for a few seconds so you can read the Krek-Stolz formula for the Ilse-Kuiper invariant using the various Dirac and Dirac type operators that are mentioned here. So the key here is that the integral is over M, and all of these things can be computed over M for a suitable choice of Riemannian metric. I mean, it's obviously easier said than done. There's still a tremendous amount of work, but at least it gives you a path to computing this invariant without looking for this mysterious co-boundary. So drawing on Sebastian Goette's expertise in these matters, we were then able to compute the full invariant, the yield-square invariant using Precht-Stolz, but of course applied to the category of four-dimension one-fold biquotient foliations. You have to realize the fibers are no longer homogeneous, so it presents an added difficulty in computing various integrals and various things. And this is the formula for the yield-square invariant. This M here, this little m here is related to what's called the half-Pontryagin class. And these dA bar and dB bar are what are called generalized Dedekind sums. They're pretty awful looking things. You're more than welcome to take a look at our paper to see the precise description, but there it is, in all its glory. And then, sorry? I thought somebody asked something. So in particular, the class of examples I mentioned earlier is parameterized by -3, -3,1, and 1LL. If you compute the yield-square invariant and you toggle the various values of L, 17, 61, etc., you get these 8 numbers which specifically correspond to homotopy 7 spheres, which are not S3 bundles over S4. Okay. So finally, we can see that this generalized construction yields a new class of examples. In particular, you get that all 28 homotopy spheres admit non-negative section curvature. Actually, if you look at the construction, admit infinitely many different SO3 invariant metrics of non-negative section curvature. Okay, so linking forms. So the point here was to show that you get even more than what you might expect. So not only do you get these other homotopy spheres, you get a lot more of the 2 connected 7 manifolds, but you get even more weird examples of topology in this case. So I'm going to talk a little bit about linking forms, and I know it's past 9, so I will, if you want me to, this is sort of a natural place to stop. If you want me to stop, I can, or I can take another 10 minutes and tell you about linking forms. Ramiro, what do you think?
I think it started 40 to 45 minutes ago, so feel free to go ahead another 5 or 7 minutes. And
okay, it should be all I need. But yeah. Anyway, you stop me when you think it's going too long. Okay. So, what is a linking form? In sort of a general algebraic definition, you take a finite abelian group, and you can, if you have a symmetric bilinear form, meaning a form on the tensor product, it's called a linking form if the form is also non-degenerate. And then, of course, you can write down a lot of these. So we say they're equivalent if there's an isomorphism of the group that takes one to the other. So you can kind of pull back one. It's kind of like pulling back a Riemannian metric via a diffeomorphism, something like that, if you wish. And we say a linking form is a standard form, so that if you choose some generator, so at this point, I'm going to switch to G not just being finite and abelian, but in fact being a cyclic group. So Z mod n, which is really what we should be thinking of, because that's going to be our H4. If you can choose a generator so that the form looks like it takes a generator tensor itself to 1 over n. And I want to point out, because it's defined on the tensor product, if I know what it does to one tensor 1, then I know what it does to every element. Okay. So as I mentioned, we are looking at the case of 2 connected 7 manifolds, which are cohomologically S3 bundles over S4, so that H4 is Z mod n. And we just said that 2 linking forms are equivalent if you can map by an isomorphism. So in the case of G, a cyclic group, an isomorphism is given by any multiplication by anything in the the group of units, the multiplicative group of units Z mod n Z star. So those are the number of equivalent forms you get. And suppose you do have such an isomorphism, say you take a generator which you call 1, and then you take theta of that to some k, which is going to be another generator. Then notice that if I evaluate this the new linking form B1, then I get k squared over n with respect to the other linking form. So that's an important point where things are, it's a square of a generator. Okay. So because the size of the multiplicative group is this Euler phi function, phi of n, these are the number of equivalent forms, forms equivalent to the standard form. And again, I repeat, the numerator is a square mod n, and it's a unit. So if you want to look for something like a non-standard form, so we have been only talking about standard forms and their equivalents. So if you have any hope of finding something like a non-standard form, and I'll explain why you might want to look for such a thing, you must land in the set of units that are not squares. So some quadratic reciprocity is going to come into the picture. Okay, so I'm gonna now specialize to the case where n is odd. When n is even, things are a tiny bit more subtle and complicated. The linking form is not going to be enough. So I'm looking at manifolds which are cohomology S3 bundles over S4. The middle cohomology H4 is Z mod n. N is, so it's a cyclic group. It's finite, and n is odd. Okay, as I just said. So if you look at the short exact sequence of abelian groups, Z to Q mod Z, you get a long exact sequence in cohomology. And in particular, you get, because we have two connected 7 manifolds, you get an isomorphism in this particular cohomology H3 of M with Q mod Z coefficients to H4 of M with Z coefficients. And you can show it's an isomorphism, and this map is called the Bochstein, this connecting map. And what that allows you to do is it allows you to define a symmetric bilinear form on the torsion part of H4 as follows. Okay. So you take two cohomology classes in H4 with Z coefficients. Bracket M is the fundamental class. And here's your definition of a linking form on H4. So you pull back of the Bochstein, you take the cup product, and then you take the Kronecker pairing, and then you land in Q mod Z. There's still some work to be done to show that it satisfies, it's a symmetric bilinear non-degenerate form. And I won't go label this point too much, but it also has, like with many things in mathematics, this is the polished end product. The original motivation comes from looking at intersection pairing of homology classes, going back to Whitney. So there is a geometric interpretation of this as well. Okay. So in the early 70s, David Wilkins, who was a student of CTC Wall, produced the following beautiful result in his thesis. So his thesis is more general, right? It's not just about two connected 7 manifolds, but I'm just taking the part that I need. So if you have such a manifold with cohomology ring is the same as an S3 bundle over S4, and H4 is Z mod n, where n is odd, then the manifold is classified up to PL homeomorphism type by the three pieces. H4, the linking form, and this is what I call the half-country eigenclass, which I mentioned earlier. Okay. So in particular, note that every S3 bundle over S4 has standard linking form. So it's probably a folkloric result, but it is a nice proof, and probably laid out for the first time in proof form by Crowley and Escher. And about 20 years ago, Neetu Kishlo and I showed that if you take a manifold which has a cohomology of an S3 bundle over S4, then it is homotopy equivalent to an S3 bundle over S4 if and only if its linking form is equivalent to a standard form. And the moment it's homotopy equivalent, by Wilkens's result, it's automatically PL homeomorphic to such a bundle. Okay. And there's one subtlety I should point out. We only require the equivalence of the linking form up to sign, because we can, changing the orientation changes the sign of the form. Okay. So what this means is, if -1 is not a square mod n, and now I'm specializing even further to the case where n is a power of a prime, just to lay out the results more cleanly, then your manifold is automatically homeomorphic to an S3 bundle over S4. So what happens in this case where n is a power of a prime? If -1 is not a square mod n, right? There are only two linking forms up to sign. If -1 is not a square, then -1 takes squares to non-squares. And these are all equivalent. So there's only one form, and it's the standard one. Okay. On the other hand, if -1 is a square, then this map x goes to -x on the set of generators. You know, it takes squares to squares and non-squares to non-squares. So if your linking form were to land in non-squares, it would stay non-standard and never be taken to the squares. I'm sorry, I'm rushing a tiny bit. I am aware of the time, right? So all I want to make is the following observation. Right? If you have a two-connected 7 manifold, if the linking form is non-standard, and your manifold is this weird space, it's not even homotopy equivalent to any S3 bundle over S4. Okay. And what I want to point out is that the construction we had doesn't just give you all these other homotopy spheres, it gives you this some examples in this strange class of manifolds as well. So appealing back to this previous result I mentioned, if you have your order of your fourth cohomology is p to the k, where p is 1 mod 4, right, then you know there exists a non-standard linking form. And then I'll just point out this last result that with Sebastian and Martin, if you look at this specific family among the ones we constructed. So we have many more examples and a much more general description, but this is very concrete. I wanted to lay it out. Then these manifolds have fourth cohomology group p squared, order p squared, where p is 5 mod 8, 1 mod 4. And you compute the linking form in this specific case for this infinite class and show that it's non-standard. So in particular, you get two connected 7 manifolds, which are not even homotopy equivalent to any S3 bundle over S4, and also emit non-negative curvature. So you get a much richer class than you would have expected just from tweaking this construction like we did earlier. Okay, so for a talk I didn't prepare, thank you very much.
Thank you, Ravi, for the beautiful jump-in talk.
And Martin, I apologize for stealing your thunder.
No, you're exactly correct. Thanks, Ravi.
And thank you, Martin, for speaking with an invisible audience.
It was an excellent talk, if I say so myself.
You have no evidence.
And thank you to the audience for your patience while we worked everything out. Are there any questions?
I do have one.
Somebody's asking for Martin's slides.
Yeah, we'll be in touch with Martin to arrange something.
So Ravi, your example, I mean, you show that these exotic spheres can be written as these sausages, right? So these are, if I understood correctly, free quotients of cohomogeneity one manifolds, right?
That's right.
Of like, are they S3 cross S3 quotients of a 13-dimensional manifold?
It's funny, I just asked the exact same question to Martin. I think. Was it yesterday or the day before?
You can say yes, just to jump in.
Yeah, so I think the answer is yes.
So if this is the case, could you hope for maybe one of the 13-dimensional examples of positive curvature to admit such a free action, giving you one of the exotic spheres so that you can put positive curvature?
No, I think the cohomology is all wrong, but also I think, as far as I know, many people have looked at the Boseikin spaces, and there is no continuous free group action on them, asymmetric.
All right, thanks.
So the best thing that is known, and there's a description in Taimanov's paper, is that the Berger space, which is sort of the first example among all the Boseikin spaces, is an RT5 bundle over CP4. And that's sort of that's the only fibration that I know of any of the Boseikin spaces over something.
Of course, it should not be known, right? Otherwise, but yeah, I understand.
I mean, if you compute the isometry group, I mean, to the extent
Yeah,
that
no
you can,
killing fields. Okay, yeah.
There's no free action. I mean, there are lots of killing fields, but there's no free action.
No free.
Oh, sorry, not, excuse me. There are lots of killing fields, but they all vanish somewhere.
Are there other questions?
It was just such a clear talk that there was.
Well, thank you again, Ravi, for.
No, I any chance I get to steal Martin's thunder.